Funding for this program was provided by the Annenberg CPB project.
I'd like to tell you the story of an accident that happened to a certain Professor Muschenbroek. At the University of Leyden in the year 1745. It was believed at the time that electricity might be a kind of fluid, and Muschenbroek wanted to make a solution of the electric fluid with ordinary water. And so a friend of his named Andreas Cuneus, who acted as his assistant, took a jar of water like this in his hand and put into it a stopper with a long nail in it. Then he held the nail up to the pole of an electrostatic generating machine, something like that one, so that the electric fluid could run down the nail into the water and make a solution with it. And then, when he grabbed the nail to pull it out of the water, he made an absolutely shocking discovery. Muschenbroek wasn't deterred at all. He just found himself another volunteer and went on with his research. But that discovery, which came to be known as the Leyden Jar, turned out to be one of the most important of the 18th century. Because before it, electricity was a mere curiosity. But afterward, it became something genuinely powerful. To appreciate the impact that the discovery had at the time, you have to understand something about the way science was done. People who did experiments on electricity, they were called electricians, formed a kind of fraternity. And like any fraternity, it had its rules and its rituals. Now, there were crude instruments at the time that could measure the amount of electricity that had been produced. But every electrician prided himself on his ability to judge the strength of the electricity by feeling the shock that it produced. It was something like a chef tasting the soup. No electrician would think of sending an experiment out without first feeling the shock. Well, before the discovery of the Leyden Jar, that was harmless. But afterwards, it was an entirely different matter. It was not a good time to be an electrician. Muschenbroek himself was the first one to do it, and he later wrote to a friend that he wouldn't do it again for all the kingdom of France. Nevertheless, every electrician had to feel the shock, with one exception, a German electrician named Winkler, who gallantly permitted his wife to do it for him. It turned out that Leyden jars were very easy to make, but it was very difficult to understand why they worked. And perhaps the most shocking thing about the whole affair was where the explanation finally came from. It came from an obscure printer in a quaint little village called Philadelphia across the Atlantic Ocean. And his name, of course, was Benjamin Franklin.
In his own time, he was known to his countrymen as the wisest and the most worldly man the young colonies could offer. In England and France, he was a legendary and wildly popular figure. Today, we think of him as a statesman who dabbled in science. He was, in fact, a serious and very important player in the history of science. And by far, his most important scientific work had to do with electricity. In the late 18th century, people around the world were fascinated by the phenomenon of electricity. In Japan, they said the people formed a line and held hands. And then, a brave soul touched something called a capacitor. Of course, that might have been just a rumor. Because in the days when Benjamin Franklin strolled the streets of Philadelphia, most of the world's scientific knowledge about electricity could fit into a Leyden jar. Professor Musschenbroek and his Leyden jars drew a lot of attention in Holland. And with Mr. Cuthbertson's devices, Professor von Marum carried on the work in the 1780s. But beyond the laboratories, particularly when it came to the famous Philadelphian, the business of electricity could be positively perilous. In fact, when Franklin tried to cook a turkey by electrocution, he almost managed to electrocute himself. In his own words, Franklin described the dangers of electricity. It seemed a universal blow throughout the body, followed by a violent, quick trembling in the trunk. A swelling raised on my hand. My arms and back of my neck felt somewhat numb. My breastbone was sore for a week. Obviously, Franklin had discovered how not to conduct electrical experiments. For the record, however, this error was as rare as the man himself. After all, he was the first to publish a theory of electric charge and electric force. The details would be worked out later, but in modern terms, where was Franklin headed?
In the vicinity of a positive charge, the electric force repels a positive test charge. An external force is needed to push the charge closer, doing work against the electric force. Positive work if the motion has a component opposite to the electric force. Negative work if it has a component along the force. And no work at all if the motion is perpendicular to the electric force. The net work is found by integrating the dot product of the electric force and the displacement vector along any path through the electric field. That net work is equal to delta U, the change in the potential energy of the test charge. Of course, the electric force is the test charge times the electric field. So the change in potential energy is equal to the test charge times something that depends only on the path through the field. That something, delta V, is called the difference in electric potential, and it's measured in volts. Electric potential, or voltage, depends only on position in the electric field. The potential difference is equal to minus the integral of E dot dr along any path connecting 2 points.
A 100 years before Faraday discovered the electric field, Franklin saw it as the electric atmosphere. In his theory, the atmosphere arose from a fluid, an electric fluid, that permeates every object on Earth. Everything, in turn, was a sponge of sorts, which might soak up the electric fluid. Franklin said that when an object soaks up too much fluid, it's positively charged with electric fluid. But if an object doesn't have enough electric fluid, then it's negatively charged. He said that positively charged objects and negatively charged objects attract each other. But two objects that are both positively charged repel each other. Franklin's terms, positive charge and negative charge, are still in use. But with better understanding, their meanings have changed. Today it's understood that there are in fact two different types of electricity, positive charge and negative charge, and that all objects in nature contain both types. Nevertheless, Franklin had realized correctly that electric charge is something that's never created nor destroyed, but merely flows from one object to another. Such far-reaching insights earned Franklin acclaim as the world's foremost scientist in the field of electricity. But it was the printing press, not science, that created his fortune and in the process spread his reputation. He'd been an apprentice on the New England Courant, a publisher of the Pennsylvania Gazette, and finally Poor Richard's Almanac, which made him very rich indeed. Though he'd turned over the shop in 1748, devoting himself entirely to science, a certain amount of printer's ink flowed through Franklin's veins for the rest of his life. But he was never content with merely reading and writing about the events of his era. And when it came to American history, Franklin preferred to go out and make it himself. But if Franklin was an important presence in the colonies, he was absolutely legendary in Europe. He was an enormously popular figure in England and France, deeply admired as a statesman, a philosopher, and a scientist who had emerged, incredibly, from the uncivilized American colonies. Throughout his life, he was also remarkably lucky. Just hours before he was to present his credentials at the court of Louis XVI, he discovered that the powdered wig and formal clothes which had been provided for him were much too small. Franklin boldly appeared in his street clothes and his own hair, and instead of being ridiculed, was instantly heralded as the child of nature from the backwoods. But even that wasn't the extent of Franklin's fame. He was also recognized as an inventor for a number of good reasons: the lightning rod and the glass harmonica, the rocking chair, the Franklin stove, and even daylight savings time. Another of his inventions, bifocals, would eventually become his trademark. Franklin was also relentlessly optimistic. Throughout his life, he saw everything as a wonderful game. A serious game, to be sure, but also a challenge of limitless possibility. How did it feel to flail a whirlwind with a whip, or to catch lightning with a kite? Franklin was the only man on Earth who could answer those questions from experience. On land and sea, he studied everything he could set his mind on, and he wrote of his studies in great detail. In part, Franklin was called doctor because of his writings on illness and the practice of medicine. Like others, he'd given electric shocks to treat palsy and forms of paralysis. However, unlike his medical contemporaries, he'd finally concluded the only benefit of shock treatment came from the exercise patients got walking to and from his house for their visits. But from the scientific point of view, the most exciting thing was, and remains, his perception of the electric fluid itself. Although in hindsight, it's not too hard to read an imperfection or two in Dr. Franklin's theory, It was the most advanced of his time, and to the extent it was correct, his electric fluid contained the sparks of things to come. Today, what Franklin saw as the electric atmosphere is seen in modern terms as the electric field. An electric field is present around any object that carries a net electric charge. Of course, if an object's positive charge and negative charge are balanced, the object is electrically neutral, and it produces virtually no electric field far away. But even beyond that, the static electric field inside any piece of metal is zero, which means a test charge would feel no force at all inside the piece of metal. And that's true even if the metal has a net electric charge. That's because the charge piles up on the surface until there's no field left inside to make it move. Of course, electrically charged conductors do create electric fields outside themselves. But inside, there's no field at all. And because there's an electric field between two oppositely charged pieces of metal, there's bound to be a difference in potential between them. But since there's no field inside, the potential is the same everywhere in the metal. So, each piece of metal is a region of constant potential. The potential difference between two pieces of metal depends on how much net charge each one has. Negative charge lowers the potential. And positive charge raises the potential. Of course, in the 1700s, Dr. Franklin was in no position to get such a clear picture of electric potential, for even its concept was unknown in his day. But he did have an enormous knowledge of electricity, which he often shared with his colleagues throughout Europe. And as the wisest American, Ben Franklin also paid considerable attention to the great minds of the past, particularly Sir Isaac Newton.
Come in.
Franklin was well aware of Newton's theory of universal gravitation, and he knew the force of Newton's gravity unites the universe by causing masses to attract each other. Franklin would have liked to formulate a similar law, a law of electric force. But it doesn't quite work, because unlike gravity, there are two kinds of electric charge. Electrical charges that are unlike attract each other, and charges that are alike repel each other. That's one reason why an ordinary battery has the potential to create an electric field.
When a battery is connected between two pieces of metal, it forces charge to flow from one to the other until the potential difference between them is equal to the voltage of the battery. That creates an electric field between them. If the voltage is doubled, so is the charge. So is the potential difference. And so is the electric field. In general, the charge transferred is proportional to the voltage applied, and the constant of proportionality, C, is called the capacitance.
Long before there was a modern capacitor, much less the means and mathematics to illustrate how one works, everyone in the world knew about lightning. But to discover the role of lightning in the world of natural science, one had to follow Ben Franklin into the study of electricity itself. Of all the 18th century electricians, only Franklin had seen lightning bolts for what they are, huge sparks of electricity, no different from the kind he could create in his laboratory. On paper, there was the basis of his theory. First, extend a metal pole, the lightning rod, from the roof of a building. Then, place a wire near the rod. In theory, the rod would draw some electricity from the stormy sky, and a spark would jump from the metal to the wire. Prior to the experiment, these instructions had been printed in England. Thomas Francois d'Albert had followed them to the letter and successfully performed the experiment on the outskirts of Paris. Of course, Franklin had no way of knowing that, as he himself stood up to face the power of Mother Nature. And in any case, when it came time to put his own theory into practice, he'd done so in a far more dangerous manner. Instead of using a lightning rod to draw electricity from the sky, he used a kite, a simple apparatus made of twigs and a silk handkerchief. And instead of a separate wire, he attached a metal key to the kite string. On the fateful night, he noticed loose threads standing out from the kite string. Then, just as he had bravely predicted, the sparks jumped. And as they zipped from the key directly to his bare knuckle, Franklin experienced a feeling he'd never forget. But in fact, Franklin's greatest discovery was not made with lightning bolts. It was made with Leyden jars. And it was here, rather than in the stormy sky, that Ben Franklin revolutionized the science of physics. Others assumed that when they charged a jar with electricity, they were adding large amounts of electricity to it. But Franklin knew better. And with his knowledge, he was the first to figure out how a capacitor worked. He realized that the electric fluid was neither being created nor destroyed. It was merely flowing from one place to another. In a Leyden jar, it was flowing from the conductor inside the jar to the conductor on the outside. In other words, the Leyden jar was the first primitive electric capacitor.
Any two pieces of metal can form a capacitor. The shape doesn't matter. The two pieces of metal can be the plates of a parallel plate capacitor, or they can be the inner and outer parts of a Leyden jar.
The electric field in a parallel plate capacitor is really due to sheets of opposite charge facing each other on the metal surfaces. The field between the sheets is constant. The two sheets of opposite charge attract each other and hold each other in place. That's why a capacitor is such a useful device. If the voltage is held constant by a battery, the charge, and therefore the capacitance, changes inversely as the distance between the plates and is proportional to the area of the plates. Franklin realized that if capacitors were connected together properly, they would create a larger capacitance. Properly meant in parallel. A series of Leyden jars, one after the other, actually created a smaller capacitance. But a parallel bank of Leyden jars proved to be an excellent arrangement, and Franklin called it the electric battery, another term that has a different meaning today. But the important thing is not the term, it's the idea. And only Ben Franklin realized that it didn't take a fancy Leyden jar to hold on to electricity. A simple pair of parallel metal plates would do. Despite its occasional inaccuracies, Franklin's work with electricity was a scientific milestone. But even so, Ben Franklin will always be best remembered as a statesman and a remarkable public servant. Here in Philadelphia, he established the first public hospital, the first public library, and the first fire department. As a delegate to the Albany Congress of 1754, he had been so bold as to propose a union of the colonies. For almost countless reasons, Benjamin Franklin was and is a national treasure, a monument to the limitless promise of democracy. In this room, with the diligence of a scholar and the moderation of a statesman, he set the course and molded the ideals for a newborn nation. But as a scientist, Ben Franklin was the greatest of the natural philosophers. Not only then, but today, throughout the world of science.
Franklin was very, very clever. It may be that his cleverest invention was the lightning rod. But he wasn't the only one to invent a lightning rod. He had a competitor in England who also invented one, and the two of them had a disagreement over a certain detail. Franklin thought that lightning rods should have pointed ends on them, and his English competitor thought that a lightning rod should have rounded knobs at the end. Well, it turns out that Franklin was right. He had the right idea. But at that time, we weren't on very good terms with England. There was something going on called the Revolutionary War. King George III decreed that all lightning rods in England would have rounded knobs. What George had tried to do was to change a law of nature by means of a royal decree. You can't do that, of course. It takes an act of Parliament. Before the invention of the lightning rod, a thunderstorm was an absolutely terrifying phenomenon. There was no protection against it. Typically, towns, when they knew that a thunderstorm was approaching, would have the church bells rung in order to try to scare it away. But of course, the church tower was usually the highest thing in town, and so typically the lightning would strike the church bell, run down the damp bell cord, and dispatch the bell ringer. The invention of the lightning rod was the first demonstration that a theoretical understanding of science could lead to mastery over the great forces of nature. The psychological impact of that discovery is with us to this very day. We'll go on with our story next time.
Funding for this program was provided by the Annenberg CPB project.